So I must say it's a very great pleasure to be here. I was actually quite convinced the conference was going to be canceled. It's also a relief after, that's my first in-person conference in, well, 2 years, like many of us, and it's really very nice. So what I want to talk about today is something very applied, so you're not going to see a lot of math. And I want to explain a little bit the context of that. This is a collaboration that started when I was still at the University of Maryland with people from the NIH, and in particular around Lavi, so the last one in, here. And Orit's idea was to try to see if we could predict the evolution of glioblastoma, and in particular the evolution to glioblastoma from another type of tumor by looking at the changes in the brain's arterial network. And that has proved, so it's a very natural idea. We're not the only one to have had it, so you'll find other works in a similar spirit. What I'll try to emphasize today are the basic difficulties that you're facing when you're trying to do something like this. All right, so as I said, this is a very natural and a very basic question, right? So your brain has a very well-developed arterial network. And of course, as you know, the brain uses a lot of nutrients, and so it has high metabolic needs, right? So you need the arterial network to provide this. And so that it works, right, that thing must be very extensive, it must be extremely robust, and it has to be adaptive. And in particular, because of this adaptive property, right, what we believe is that if there is a change somewhere in the brain, so a tumor locally, for example, then that should lead to changes everywhere. Because the arterial network should adjust to compensate for the different needs of the various of the regions. And so then we turn to glioblastoma, right, that are a very big topic in brain cancer. Those are the very nasty ones in the sense that you don't really expect to survive them, and the issue is fatal within a few years usually. They also very often do not start at glioblastoma. So you start with another type of brain cancer, one that is more benign, and then at some point it evolves into a glioblastoma, and then it's mostly very bad news. So there's a lot of interest to try to understand them for this reason, and to try to detect them, and detect them as early as possible. So this is basically the question, right? Can we see from changes in the brain arterial network that a benign cancer changed to a glioblastoma, and can we predict what's going to happen, how fast it's going to happen afterwards? Now, of course, I won't be able to answer the question fully, right? I'll just give a few preliminary results here. As you will see, one reason we cannot answer this question fully is lack of data for what we want to do. All right, so this is just a rough idea that there's also different subtypes of glioblastoma, right? And they have very different distribution in the brain, and they behave in a very different manner. So what you see here is an average density, right? So they took MRIs of various patients, right? And looked at where the tumor cells were, and the higher density, so the red, right, indicates where you have high correlations between patients concerning the localization of the tumor. And you see that for some subtypes, it seems to be all over the place, and other subtypes, you have more correlations. All right, so what do we want to do if we want to try to do a study like this? Well, the first thing, and that is the big issue, we need to have high-resolution MRIs of patients' brain. And this is too bad because, as you will find out, the current protocol for brain cancer patients does not ask for high-resolution MRI of patients' brain. So basically, the first thing we need, we won't have it in most cases. That's something, of course, I had no idea of when we started on this, right? This is the kind of things you find out one step after another. We ended up having relatively complete data for one patient. So this is what strongly limits the kind of conclusions that you can draw for this kind of study at the present stage. They do MRI of patients, right? They're just low resolution. And another question will also be, even for that one patient we don't have enough high-resolution MRIs. So the question is, if you have one good high-resolution MRI and plenty of low-resolution MRI, how do you use the low-resolution MRI to still do what you want to do out of all of this? All right. So then what do you need? First of all, there's a lot of image processing. Right? What you need to be able to have is a reasonable software that if you feed it an MRI, right, it will give you back some sort of arterial structure of the brain. Okay. And I'll discuss a little bit what we've done there, right? This is not very hard, it's just extremely time-consuming. And of course, you still want to be able to handle quite a few of those MRIs, right? So you want human intervention, to be as low as possible within this sort of techniques. And the second step that has proved just as frustrating as the others, right, is now we would like to understand what the blood flow is like. Because we believe that changes in the structure of a network, right, they are there because there are changes that are needed for the blood flow. So that's what we want to see. So we need to be able to model the blood flow, given the result of the previous step. And so I'll go slowly over this kind of things. Again, there's no big math here, right? But just tricky modeling. All right. So what type of data did we have available to do all of this? So I said for patients, right? We didn't have a necessarily very good high-resolution MRI or MRA. But we had high-resolution, there are data sets for healthy people with high-resolution MRA that we can use. And so those are typically those first two, right? So we used a study from 2013, right? Around 60 people in it, and MRA up to 400 micrometers, and then more recent studies, 2017, 2018, right? Just one person, all right? But with a very high resolution MRA, 150 micrometer. And all of this typically uses motion correction, so it's a fairly heavy type of machinery that you have to put in place, right? With this kind of resolution, you can't have even if you ask people to stay as you know, please don't move your head, right? That's not going to be good enough for this kind of resolution, of course. So, so it's a very, from the technical side, which I know nothing about, I just saw the thing one day, right? It's a pretty expensive equipment. Then the reason we started this is initially so the NIH is a big, so those are the National Institute of Health, right? And it's a very nice idea because, for example, you have a very big campus near Washington, and they have a hospital and they have a research center at the same place. So they actually see patients. And so initially, that's what made me hopeful that we would have access to the data and the right type of data. And so indeed, the third data set, right, was a group of 400 patients, which was reasonably optimistic. The problem, as I was saying, is out of this group of 400 people, only one actually had a high-resolution MRI at 400 micrometers. And all the others had only very low images. Now, this is something we found out right in the middle of it. So keep that in mind whenever I'm saying anything. We were not able to actually test the conclusions of this over a large enough group to validate them fully. So that's what we used. So immediately you see the issues, right? You have different data sets, they have different resolutions, they use different parameters from the imaging, they use different equipments actually. So already putting all of them together is not completely obvious, right? On the actual patients, so on the actual thing that we want to study, we have only very limited data. And in particular, I have one time series MRI on one patient, right? That's it. So as I said, this is essentially a proof of concept at this point, nothing more. All right, so let me describe very, very briefly the software to get an arterial network out of the MRI, right? And there's essentially roughly 5 steps, and I really pushed that we use well-known algorithm for each step instead of trying to do something on our own, which I think was a lot safer. So you need to do the raw image registration first, right, to get to something that you can actually use. Then you want to do a filtering. Then the key step is, of course, the skeletonization, right? So that's where out of the image you want to get curves, right? And here we used a very well-known now curve skeletonization algorithm. What you get out of that, there are some disconnected branches. So the algorithm was typically not able to connect everything. So you need a manual error correction step. The way this is done, the algorithm identifies the disconnected branches. So we had a student that was going there, and then the algorithm was showing different branches, and then the student was trying to see if this was an obvious disconnection or not. And branches that we could not connect, we removed. And then you get to a final graph representation after the skeletonization. Right? So the final graph representation, this is what I'm going to show you afterwards. What that means, right, is you need to, the skeletonization will still give you a sort of weird curve, right? So You need to identify its beginning, its end, its length, some measure of curvature as well can be useful, things like this. And so all of this is on GitHub. It's not very user-friendly, as you can imagine, but it's still, you know, you can still go and play with it if you want to. All right. So just a few more words, right, on the vascular filtering. Again, there are a few subsets here. Again, we used a very well-known method, right? So you have a thresholding, which removes a lot of the noise and things like that. And then this allows to split the image into connected components. And this splitting is very key because then you apply a variational growing technique in each of the component. And you absolutely don't want to do that on the whole thing, otherwise it goes everywhere. But having a very localized region, then the result is not too bad. But initially, we just tried to use the variational region growing on the whole thing, and it was a total mess. All right, a few more words as well on the graph representation and a little bit on brain's anatomy. I had no idea about what the arterial network in the brain looks like, right? So I still remember the first meeting, and I show up and I said, well, it should be a graph, right? So right, you have big arteries, they arrive in the brain, and then they split, right? Logical. But it's not like that for a good reason. So in particular, you have something which is called the circle of Willis, which is a circle. Right? So not a graph. So what we do is we take out the circle of Willis, which is the first stage of the arterial network, right? And then we have various graphs from the circle of Willis downwards. And the graph is pretty much what you would expect, right? Each node in the graph is a bifurcation point, so it's where a vessel is splitting or finishing in the sense that we couldn't identify anything further, right? And the edges correspond to the center line of the skeletonization that we had. And as I said, we completely discarded the branches that we couldn't connect to the network. All right. And typically from the circle of Willis, as I said, you're going to have different graphs, right, which we use this kind of initials. If you don't know much about brain anatomy, which is still roughly my case, this is, well, those are just different regions in the brain, and that's it. All right. So here's a little bit of an example of what's going on. All right, so the left, right, is your magnetic resonance image, right, after registration. So this is the sort of stuff that you have, right? And the goal is to end up with what is here. Right. So that's what the software has to do. So, okay, you do segmentation, you identify the center lines, right? You identify the circle of Willis, and here you see that on this patient the tumor was here, right? You get to something like that. And if you zoom, you have something of this type, okay? And out of that, you can get a graph representation by identifying the terminating nodes, then every bifurcation nodes up, and reconstruct the graph. And on the edges, you can also encode various properties like an estimated length, right? Now, estimated length, you see that those things are not straight, huh? As would be expected. So it's worth what it's worth, right? We even estimated the curvature, which again, it's what it is, right? It's an estimation. But this is what the software is doing, and I'm not spending a lot of time on this. The poor students who were involved in the project did spend a huge amount of time in coding that. And then you can do various statistical analysis over the graph, right? So here we showed, for example, the distribution of the branch length, right? Depending on which graph you had, so which region of the brain, where you start from for the circle of Willis, right? And you see that there are differences, but they are reasonably homogeneous, right? Now, the graph level is a little bit all over the place, right? Which is what you would expect, because you're probably missing a lot of the smaller blood vessels with this sort of things, right? And this also allows us comparison of some of those statistical properties between the various data sets that we've been using, which is useful, again, as a validation point. Here I'm just looking at 3 compartments out of all of them, right? And you see that, of course, the resolution plays a very big role, right? So to remind you, the first data set, the right data set, resolution was 400 micrometers, right? The spec data set is 1 person, but 150 micrometers. And our GBM patient was 400 micrometers again. And so the number of branches, for example, it's very, very telling. Of course, with a better resolution, you have a lot more branches. No surprise there. You see that our GBM patient, however, who had the same resolution as the right data set, it fits reasonably well within the statistical variation of that data set, right? So that was certainly reassuring. Right. So here's the same compartment, right? One patient on the right data set, one the glioblastoma patient, and the one patient from SPEC, right? Just to give you an idea. Again, they are reasonably similar, right? It's not completely crazy. Very, very obviously, they are not identical as well. And this is not a big surprise, by the way. This is probably not only an artifact of the data sets themselves. Doctors don't really expect every one of us to have the same, the exact same arterial network, even from a topological point of view. All right, so this is another compartment, and it's pretty much the same type of conclusion, right? Now, the next thing is they, of course, wanted to do blood flow simulations. And initially, right, as with the rest of that study, I was extremely naive. So I thought, sure, right, we're going to have a good representation of the blood vessels. And then I know plenty of good people who have done, you know, a good fluid structure model. we are going to pick one of those, and there's going to be a lot of work again for the students to implement them, but this is going to work, right? And when I saw the result, it was obviously not going to be working, not like that. So of course, already the modeling is a very complicated business, right? Because blood is not a simple fluid, right? It's non-Newtonian, viscous, especially at the low scales that we are going to be looking at, right? Maybe less viscous at the larger scale, so how do you separate that is already an issue, right? As I said, you need a fluid structure model because the vessel's boundary are not rigid. And the elasticity or the dynamics of the boundary of the blood vessels, it was shown to play a big role. And all that means that those models are very complex. And if you want to use them, and if you want to solve a 3D flow, you realize that you need a very good geometry. And if the geometry that you have is not even very accurate, right, what you're gaining by using this kind of very complex model is probably very debatable because you have no idea where you are. And of course, the last point is we have a pulse, right? So blood flows are not steady flow. So on top of that, you would have to calculate, I don't know, periodic solutions or something like this. So when we ended up with this kind of representation, right, we had an extensive discussion, but then I realized the initial plan was absolutely not going to work. So then we decided to take a very simplistic model, which is slightly crazy, but fits well with the roughness of a representation that we got. And so I ended up looking at very old engineering textbooks, right, and pipe models. Right, so this was very important, and it's still used very extensively. And it's basically, you know, you have water pipes, right, and they split, and you need to be able to calculate the pressure and the flow at various parts of the pipe. And so you have models like that, and we chose to use what is called as the Hazen-Williams equation. And what this is an estimate of steady flow in a pipe. And in particular, it tells you the loss of pressure from the head of the pipe to the tail of the pipe based on the flow, right, which is Q, the diameter of the pipe, which is D, and its length, which is L. Right? And you have a few parameters there, the roughness coefficient C, right, and what is called the flow exponent K. And as I said, this was initially used for water, but of course you don't need to keep the same coefficients. And now the issue here is it's not clear that this is capturing correctly the viscosity of the flow. But, all right. However, one advantage of this sort of model is you don't have to use the same coefficients for each part of the arterial network. And so with this idea that the flow is very different in the larger blood vessels versus the smaller blood vessels, right? What we did is we divided the arterial network into compartments, depending on the level of the graph where you were, right? So the estimated diameter of the blood vessel was useful for this. And we use different constants for each compartment. And after that, solving this is a relatively simple linear programming type of things, right? What you end up having is a set of equations from the beginning to the end. You still need to have some sort of estimates, right? Like terminating pressure, for which we really don't have any good measurements because we know very, very little. So it's still not as easy as it sounds, right? So this is what it looks like, right? You have an equation on each edge of the graph, right? You assume that the pressure is the same on the nodes, right? And then on each edge, right, you have this equation. So you put the continuity of the pressure, right? And of course, you have conservation of the flux, right, at each node. So all the incoming flux are equal to all the outgoing flux. And if you have a graph, right, then this has a unique solution. So provided you know how to resolve, again, the circle of Willis stage, then the rest of it, you can solve that. Right. So this is what our choice of parameters, right? So K was uniform, and then the roughness constant was changed. And as I said, we took 4 compartments, right, depending on the diameter of a radius of each blood vessel. You see that they are not completely different, right, from one to another. And the big issue was choosing the terminating pressures because, again, we basically have no data. And, you know, I should say the more we went into that, the happier I was that we didn't try to do 3D flows from the start, because doing 3D flows without even a terminating pressure, I don't see what we could have done here. All right. So to fit all of that, we used another study by Blanco, which had a detailed arterial network of the whole body, actually. And that was based on mostly on existing literature and autopsy. And so they had around 2,000 blood vessels in the body. And for the part that we're interested in, right, the brain, they had about 140. So a lot less than what we have from the MRA, of course, but still. And then what they've done is they tried to be reasonably accurate, so they did 1D Navier-Stokes simulation on that. And that's what we used to fit the parameters, right? So we truncated our network at their level, and then that allowed us to optimize the C and the K, right, by using their terminating pressure. And there was another benefit to this. What we saw is that there was almost a very good relation between the terminating pressure they were obtaining and the path length on our graph. And so this suggested that this was a good way to determine the terminating pressure when using the full graph now, by simply imposing this relation. So this is what you have, right? This is what I'm talking about. So this is the pressure, right? And this is the path length. And you see that it's not perfect, but it's not that bad. And so that was very, very useful because, again, we needed to fix the terminating pressure, and now we could use this, this relation. And so this is the kind of comparison that that we had now on the full graph, comparing it. So you see that we have a lot more points, right, through the simulation than a very severe model. We have more blood vessels. But when the points are comparable, it's actually not bad, right? Some of them are a little bit more off, right? But not so much. And you see that, especially if you compare the two pictures to the right, the qualitative agreement between them is quite good. So we were not unhappy about the result, okay, given the quality of the data that we had to start with. All right. And then we can do what we wanted to do from the start, right? Which is actually look at all of this. So this is now some actual simulated flow on the data set, right? The left is this one patient with very high resolution, and the right is, again, one patient for the still healthy, right, from the other data set. You see what it looks like, okay? So pressure goes down. It's relatively, yeah, so what I should say is that it's more visible here. The color of the, oops, sorry. The color of the nodes, right, is the pressure. The color of the edges is the velocity. Okay, so this is what finally we can do. And we also performed some sensitivity analysis, which was a first step in trying to understand whether we could detect adaptivity with this, right? So, so what we've done is we've reduced the radius of a certain number of branches, right? Thinking, well, that might stimulate the effect of having a tumor, which is compressing everything locally, for example. And we did 3 settings, right? We picked up just 3 to 10 branches anywhere in the network. Then we picked into a subtree, or we actually picked a subregion. Right. And so you see you see the changes here, right? So this is the first case, and with 30% reduction in radius, right, when this is done almost everywhere, there's not a big effect, right? Of course, with 70%, now you start seeing something. This is the subtree, right? And with the subtree, actually, you see something a lot better because you see the localized effect, right? And this is the subregion. And again, you see, so there's a few changes, right? But you see that this is reasonably robust. With a 30% reduction, it's not like so much is going on. Of course, with a 70% reduction, now it's more striking. So this was reasonably, let us be reasonably optimistic about what we could see with that. All right, so now let's go to the actual patient for whom we had the full data. And let me describe a little bit what happened to her. So she was admitted to the NIH in 2008, right, with a brain tumor. It was a low-grade neoplasm, so, and she enrolled in a clinical trial. And for 4 years, essentially, this was what it was, and then it started to change, right, to a mixed low-grade, high-grade. High-grade is where you're going to glioblastoma, and this is the bad news, right? So when she went high grade, she had radiation therapy. Doctors know that they have to move aggressively in a case like this, right? And after further exams, surgery, right? And as is relatively typical from what I understand in those cases, that only postponed things a little bit. So essentially a year after the high-grade neoplasm was back, she had another surgery. And yet a year after, again, the tumor transformed and she died. And this seems to be a relatively typical evolution of the disease, unfortunately. We have the first surgery. So we have a series of MRI brain perfusion, right? But those are 1 millimeter resolution, right? So they are really not that great. Except one that was done on the time of her surgery, right? In 2013. So we ended up having 5 time points that were that we could use from 2010 to 2013. And what we did here, right, is we used the arterial structure that we could get out of the good MRA. And it was not so great because the tumor already evolved, so the arterial network was already damaged in some part of the brain, and you're going to see that. And then we used the other data sets that we had to try to supplement this in between. All right, so this is essentially the end, right? So you see 2000, the red parts are the bad ones, right? The high-grade lesions. So you see 2012 and 2013, then there's surgery, but in 2014 it starts again, then there's another surgery, 2015 it starts again, and you see every time in a different region, right? And 2016 is the last one before death. All right. So this is what we ended up having from the high resolution MRI. Right. So you see the circle of Willis, right? This is not a graph. This is not a tree, right? You see the circle of Willis at the root. And you see that after the circle of Willis, you have trees, right? As I said, it's not as detailed as we could have hoped because having the high resolution MRA when the brain was already very, very much impacted by the tumor, well, the resolution was not enough then. Plenty of the blood vessels were not super visible. But we can still do blood flow, right, on that, so that's what we've done. So this is the result of a blood flow calculation in 2010, right, when everything was okay. And you see that it doesn't look bad, okay? And in particular, it looks reasonable in each subtree, and the pressure is not the same, right, in every part of the brain. You see that here it's considerably higher than there. Again, this is not something that was surprising for doctors. This is essentially something they are expecting. Okay. This is the second step, right? And you see that here something happened. It's definitely not the same flow anymore. And here as well. So you see that it changed basically everywhere. Okay. Only this part has remained essentially untouched. So this is already, and you see that the pressure has increased pretty dramatically here. And this, as we understand it now, is a very big warning sign that something bad is already going on. Right. And you see the further evolution. So it's fairly clear in that case that the blood flow pretty clearly follows the evolution of the disease. Of course, we know the result, and as I said, it's only one patient, right? So it's hard to say if we do that in a blind testing, can we actually accurately detect the patients who are going to have an evolving glioblastoma from the others, right? This is what we would like to say, and this is what we cannot say because there's only one. Now, if we had 50, right, and we had seen the same thing on the 50 patient with glioblastoma and nothing at all on the ones without the glioblastoma, then we could have said fairly accurately, yes, this is going to be working. But having only one patient, it's impossible. So we did a first paper with this, and then we thought, how can we go further? Because without data, and then the next idea was to say, well, actually the NIH doesn't have more data on glioblastoma patients. What they do have is data on another type of patients that are sickle cell patients. And then we thought, okay, that was not the original goal, but maybe it is worth spending a little bit of time on that. And I'll take 5 minutes to show to you what we were able to do. Unfortunately, at that point, Henri took a job in Israel in a startup. So I'm not quite sure what's going to happen with the end of this study, but because I don't have access to the data. But at least on the sickle cell, it is working reasonably well. So let me explain that. This is a much better, so sickle cell is a blood disease, right? So on the other hand, everyone believes that the blood disease will have effect on the evolution of the blood vessels. Right? And here we have a good data set. So we have plenty of patients, and we have at least 3 data points for each one of them. All right, so here's the evolution, right? This is one patient. Everything is anonymized, of course, right? And again, this is the evolution of the mean radius, right? Of the various blood vessels in this compartment, right? Along the 3 data points. You see that, well, things happen, right? Obviously. So we were very happy with this till we did the same with a healthy patient. And then it seems even more stuff is happening. Now again, it's not necessarily a big surprise for doctors, right? Arterial networks are not frozen in time. Especially at the level of the small blood vessels. This is something that they do obviously change in time, right? The topology remains the same, okay? But the evolution of a radius. So, right, this is now the histogram, right? Of some of the patients. So the first row are healthy people. The bottom row are people who are sick, so with sickle cell diseases. Up to there, you see that it's really all over the place, right? But if you work a little bit more, and what I actually did at that point is I had one student run a clustering algorithm to try to make sense of the whole thing. And it turns out that if you're looking at the right LP norm of the arterial network, then you have a pretty clear separation between healthy and non-healthy patients. And this is the so this is the case, right? So here I took 5 patients of each, right? So I'm using an L 0.5 norm, and you see that here you have a fairly obvious threshold at around 4,500, right? Except for one healthy patient that took us a little bit of time to understand what was going on with him. And the problem is that patient had 2 MRI at very short time interval. And because we are calculating rate of change, we are dividing by the time difference. And so this gave number that were completely artificially high. And probably just because we are seeing noise here, right? So this was not a real change. It was just if I'm doing 2 exams very close to one another, there's always a little bit of noise, so you're always going to be a little bit of change, right? And that change, if you divide by the time difference between the exam, of course, you can blow up the numbers completely artificially. So now then we learned how to remove this kind of cases from the data set. So that was fairly optimistic, right? Again, I'm not so sure where this is going now, unfortunately. And it's essentially time to conclude as well. So I think the conclusion here is yes, current brain imaging, first of all, it can be used to get a relatively accurate representation of the arterial network. And then, at least at the qualitative level, maybe not at a fully quantitative level, but at a qualitative level, this representation is good enough to understand changes in blood flow in those networks. So for sure, there's a lot of potential here. To go further, as very often in this kind of applications, we need more data. And there needs to be a bit of a push, right, so that patients actually receive more accurate MRI and MRA in cases like that. And some doctors are aware of that. Of course, it's very, very hard to change a medical protocol. And those things are expensive, as I said, which is another reason why it's not that easy to do. If we could have more data, then maybe we could actually learn a lot more about the disease thanks to this kind of techniques. As it is today, I have to remain careful. Again, I can only say this is promising. Thank you very much.
Very nice talk. But I was wondering if the wood flow, is it pulsative? There are pulses, or is it continuous? And whether these oscillations may affect on the velocity and pressure calculation, and whether they may also, in turn, determine how it's going to affect also the...
Yeah, by calculating steady flow, for sure, we're making a mistake. And if we, I have it. In particular, if we were trying to actually solve Navier-Stokes with the fluid structure interaction, I think you would see a very big difference between trying to calculate a steady flow and actually trying to calculate the flow with a pulse. Because of the simplistic model that we are using, I'm not sure this matters so much. The model is already very wrong. So we probably just have some, you know, I wouldn't say it's more than qualitative, right? I wouldn't expect that we can estimate the blood flow of a pressure at plus or minus 10%. Even though we have a good fitting with an actual Navier-Stokes calculation, right? It's, as you know, it's always easy to fit things, right? That doesn't mean that they have a very good predictive value. So I would only take that as a qualitative understanding. So if the pressure goes up, it probably goes up, right? Whether it goes up by as much as what is shown from the simulation is, I don't know.
Hi. So I have a practical question.
Yeah.
In that example of that poor person who died in 8 years,
Yes.
The topology of the blood flows of the vessels was the same all the time. Now, in my head,
Yes.
naive, I've never thought about this. I would think the cancer disrupts it and breaks it. So can you clear that up for me?
Yeah. So probably. But we couldn't see that because the first MRI we had, the cancer was already there. At the level and the consequences, this is not as precise as we would have expected it to be. And if I'm going back. So this and that have the same resolution. And yet this is so much less precise than this one. It would have been so helpful to have an MRI before the glioma was there. What you're describing probably happened. It's just happened before we could see it.
Angiogenesis is described in GBMs. That's something that people expect.
Yes, that's what. But more than angiogenesis, it's probably moving the blood vessels, crushing some of it. So locally, you probably at the scale of the small ones, you probably have quite a bit of changes. Whether this leads to angiogenesis somewhere else could be. I'm not really competent to answer that, but for sure, I think there are changes in the topology, right? In the sense, I don't believe you keep the same arterial network. You probably at least lose some blood vessels in some regions.
Losing, maybe you can follow by making your diameter go to 0 in your model, while creating new things you wouldn't, right?
The problem is measuring it, right? It's not that our model is trying to predict the evolution. It's just observing the evolution and trying to draw conclusion out of that evolution. But if we cannot see, we cannot see, right?
Okay. Any more questions?
So thank you very much for the talk. I got a question about the poor sick patient. Could you maybe go to the time evolution of her blood vessels again, please? So it was this middle right part that where the pressure
Yes.
went up, and do you know whether this is actually the part where the tumor was?
Yes, I think the tumor was actually here.
Ah, okay. Okay, that's also quite interesting.
Yeah.
Maybe also to compare it with other patients if there's more data, of course.
Yeah. You know, as I said from the beginning, that's the flow in all of us, right? What you would need here, you would need to have 400 patients. You would need to do that for 400 patients, and then we could start talking about what kind of solid conclusion we can actually draw.
Sure, thank you.
Thanks. I think I'll just move to the internet questions if there's some, because we're a bit behind.
So there is a simple question. Would this help to monitor or to find a way to deliver drugs to the brain tumor?
That's a good question. I don't know, actually. Well, knowing a little bit what the arterial network is like could help, I guess. But modeling the blood flow, probably not. Because anyway, right? I mean, the question is whether there is a flow or not if you want to deliver the drug, I imagine.
Okay. Okay, so I think we'll stop here. Thanks again, Pierre-Emmanuel.